This one's pretty easy if you have the calculator and you know what's going on. So, the rate at which rainwater flows in a drain pipe is modeled by the function r. The rate at which rainwater flows. Okay. Cubic feet per hour. That cubic feet per hour. T is measured in hours and T is between 0 and 8. The pipe is partially blocked, allowing water to drain out the other end of the pipe at a rate modeled by D of T. And then there's all of that there. Cubic feet per hour. For 8, it's a T between 0 and 8. There are 30 cubic feet of water in the pipe at time T equals 0. How many, for part A, how many cubic feet of rainwater flow into the pipe during the 8-hour time interval 0 to 8? So, it's asking for the volume. We have the rate underneath. We have the rate at which the volume changes. I don't know why I said underneath. I do know why I said underneath. But it says how many cubic feet of rainwater flow into the pipe during the 8-hour time interval. That's using the volume, or getting the actual volume. But it's not the volume that's already in there plus what flows in. It's just what flows in. That's what they're asking. So to get the actual volume, you integrate. You get the area underneath the rate curve, and that gives you the net change, the net displacement. But this is positive for T from 0 to 8. So this is always increasing from 0 to 8 hours. It's in hours, right? So we can just integrate from 0 to 8. So for part A, we take the integral because the area underneath the rate curve of this is the actual change in, or the net displacement, or the net change in volume, if this is the rate at which volume changes. And it is. So I have the 20 sine t squared over 35 dt, going from 0 to 8. And you can use a calculator, and that gives you 76.570 cubic feet. And there you go. It's pretty easy. Pretty easy. The key piece to remember is if you have a rate function, then you can get the net change by taking the integral. You get the area underneath. All right. Part B is the amount of water in the pipe increasing or decreasing at time T equals 3 hours. Give a reason for your answer. Well, we don't have a volume formula. We don't have a volume function, but we do have the derivative. And if we're saying that the volume is increasing, then that means the derivative should be positive. However, there's two rates that we're concerned with in this problem. The rate at which stuff is coming in and the rate at which stuff is coming out. So, the total rate of change of the volume, that's given by R of T minus D of T. That's already the derivative of the volume that's in the pipe. So what we can do is just plug in 3. You plug in 3 and see what you get. And I think you get a negative number like that. So the total rate at which the volume is changing is a negative. So this is less than 0, which means the volume is decreasing. The is the amount of water in the pipe, or decreases, increases or decreases. So the rate is negative, which means the volume is, or the amount is decreasing. So there we go. There we go. That's part B. Part C. At what time T equals 0, less than or equal to, okay, so what time T is the amount of water in the pipe a minimum? So if I had, part C, if I had a volume formula, V of T, then I would take its derivative, set it equal to 0, find critical points, and then check those, so set it equal to 0 to find relative extrema, and then check to see if it was a minimum or maximum. I could plug in stuff to my original volume formula, and then figure that stuff out. I would also have to check my endpoints because this is on a closed interval from 0 to 8. So the first thing I want to do is figure out a volume formula. At what time t is the amount of water in the pipe at a minimum? Justify your answer. Okay, so the volume formula, remember we start out with 30 cubic feet, I think, right? There are 30 cubic feet of water in the pipe at t equals 0. So I have 30 feet, or 30 cubic feet, plus, well, we just said it before, the integral of the rate will give us the net change in like the amount that we have. So I can say from 0 to some t value, from 0 to t of r of t minus d of t. Because that is the rate at which the volume changes. So if we integrate, that would get the actual volume. So there we go. We have that. But if I take v prime, which is what I'm interested in this problem, this goes away, and I just get, well, actually I should change these. So if I took the derivative of an integral, they like cancel out because they're inverse operations. So we have r of t, which is what we had before. We knew this, d of t. But now I want to set it equal to 0. And the whole point is so I can find any critical points. And then I'll check t equals 0, and I'll plug that into here. And then I'll check t equals any other like critical points, and then I'll check at the end t equals 8. So here I'm setting it equal to 0, and I'm solving this in my calculator. So I have like 20 sine t squared over 35. I think that's what it is. Minus, actually change it to plus. And then I'm going to write down that. And so I can solve for t in my calculator. And then what do I get? I get those two values. So now I need to know what v of 0 is. V of 3.271658, and also v of 8. Because those are all my points where I possibly have a minimum or maximum. And what will happen? What will I do? Well, I can plug it into this. I feel like that might have been the trickiest part to come up with, but we just have to remember that if we have a rate function, we can integrate and get the net change in whatever we're talking about. So here, you think, wait a minute, what do I do? I can just plug in my t value. Here, I plug in 0. That just gives me 30. That's easy. The area underneath this curve from 0 to 0 is 0, and then plus the 30. This part, for this number, we can plug that in and do that in the calculator. Take the integral in the calculator and then add 30. And I get 27.964561. And then the last part, you can plug it into the calculator when you plug in 8, and you get 48. So it's just increasing the whole time. 48.5, or it seems to be 43686. So the minimum is the minimum y value, and that's there. Okay. The real explanation for why it's a minimum is because that's when the derivative equals 0, and that's where you're allowed to have relative extrema. And then we plugged in the x values, or in this case the t values for the relative extrema, and then found the y values. And we also plugged in the endpoints. And it was just the lowest value, so that's the justification. We know this is minimum because that's when v of t has a critical point, and it's the smallest value out of all three, including the endpoints, when you plug in stuff. So that's why it's a minimum. And then part D, this is actually really, really easy. The pipe can hold 50 cubic feet of water before overflowing. For t greater than 8, water continues to flow in and out of the pipe at the given rates until the pipe begins to overflow. Right? But do not solve an equation involving one or more integrals that gives the time w when the pipe begins to overflow. So it begins to overflow at 50. So it's really just, well, 50, we set the volume to 50, and then we just write the volume formula that we had already, which is here. That's it. That's all we're doing. So 30 plus, except for they say the time w, so I change that to a w, and then I have Oops. That's all that there is for that problem. Just plugging in that stuff. And it says don't solve it, so there you go. That's it. Good day.